Have you ever wondered what's actually happening when you type docker run? I mean, really happening, under the hood, at the kernel level. Here is a mind-bending fact. When you run a container, you're not starting a virtual machine. You're not even starting something fundamentally new. You're just asking the Linux kernel to lie to a process about what it can see. By the end, you'll understand why containers are so much faster than VMs, why they're less secure than you might think, and most importantly, you'll be able to see the actual processes running on your host machine, proving that containers are not as isolated as they appear. Let's start with why we're even here. Imagine you are running a web server in the early 2000s. You want to run multiple applications on one physical machine, but you don't want them stepping on each other's toes. Different library versions, different configurations, different everything. And your options were basically buy more servers or create virtual machines, with all the overhead that entails. The Linux kernel has had isolation features for decades. It started with something called chroot back in 1979, literally just changing what the process thinks is its root directory. Then came LXC, Linux containers, in 2008, which just added more isolation primitives. But Docker finally packaged all these kernel features into something developers could actually use. They made it simple, portable, and, most importantly, they created an ecosystem around it. But Docker didn't invent containers. What Docker did was make existing Linux kernel features accessible and standardize them. Today, even Kubernetes doesn't use Docker anymore. It uses containerd, the underlying runtime. The three pillars of container isolation. When you run a container, three kernel mechanisms work together to create that isolation magic. Think of them as three legs of a stool. You need all three for stability. First, namespaces control what a process can see. They create isolated views of system resources, the process tree, the network stack, the file system mounts, even the hostname. A process in a namespace believes it's the only thing running on the system. Second, cgroups control what the process can use. They limit CPU, memory, disk I/O, and network bandwidth. Without cgroups, one container could starve all the others of resources. Third, file system layers give each container its own file system, built from layers like a stack of transparencies. Change something in the container, the change goes in a new layer on top. Now, let's see why this is fundamentally different from virtual machines. Here is the most important concept in this entire video. Containers share the host's kernel. VMs do not. With a virtual machine, you have a hypervisor creating actual virtual hardware. Each VM runs its own complete operating system with its own kernel. When a process in a VM makes a system call, it goes to that VM's kernel. The VM's kernel then has to talk to the hypervisor, which talks to the host kernel. That's a lot of layers. With a container, when a process makes a system call, it goes directly to the host kernel. There is no translation, no virtualization layer, no separate kernel. The host kernel just uses namespaces to filter what the process can see and cgroups to limit what it can use. This is why containers start in milliseconds, while VMs takes minutes. This is why containers use less memory and CPU. But this is also why containers are less secure. A kernel vulnerability affects all containers on that host. They are all using the same kernel. But who decides how all this works? That's where the OCI comes in. The OCI created two specifications that every container runtime must follow. The runtime spec defines how to run containers, what syscalls to make, how to set up namespaces, and how to apply cgroups. The image spec defines how to package container images, the layer format, the manifest structure, and the metadata. This is why you can build an image with Docker and run it with containerd, Podman, or any other OCI compliant runtime. They all speak in the same language to the kernel. And this brings us to an important production insight. Kubernetes used to use Docker as its container runtime, but starting with version 1.24, it dropped Docker support. Because Docker was actually too complex. It was a whole toolchain when Kubernetes only needed the runtime piece. So, Kubernetes now uses containerd directly, cutting out the middleman. Alright, enough theory, let's get our hands dirty and prove everything I just told you. We're going to run a container and then peek behind the curtain to see what's really happening on the host. First, let's run a simple container. Looks normal, right? Just another container running. But now, let's check the process tree on our host machine. Wait, we can see the Nginx processes directly on the host. They have regular pits, they're using host memory, they are scheduled by the host kernel. The container isn't hiding them at all, at least not from the host perspective. Let's take this further. Let's prove that the container process is actually a child of containerd. The Nginx process is literally a child process of containerd shim, which is a child of containerd. It's not in a separate virtual machine. It's just another process on our Linux system with some namespace magic applied. Now, let's see namespace isolation in action. Watch what happens with the hostname. On the host, let's check our hostname. Now, let's check the hostname inside the container. Okay, different hostnames, but they both talk to the same kernel. The container process is in a UTS namespace that gives its own view of the hostname. From inside the container, it really believes that the system's hostname. Let's look at one more thing, the file system layers. This is where Docker gets really clever. See those layer IDs? Each one is a file system layer. When you make a change in a container, Docker creates a new layer on top using a copy and write file system. The base layers are read-only and shared between containers. Only the top layer is writable. This is why you can run 10 containers from the same image and they only store the difference. It's like having 10 copies of a document but only saving the edits. Okay, before we wrap up, let me show you the two most common mistakes that trip people up. The container exits immediately. This confuses so many people. The reason? The Alpine image has no CMD or entry point that keeps running. A container isn't a VM that stays on. It's just a process. When the process exits, the container stops. The second gotcha is permission errors with user namespaces. The file is owned by root. This is because, by default, containers run as root inside their namespace, which maps to root outside. In production, you need to configure user namespace remapping to avoid security issues. Fine, let's recap what we have discovered today. First, containers are not virtual machines. They are isolated processes using kernel features, namespace for isolation, cgroups for resource limits, and layered file system for storage. They share the host kernel, which makes them fast but also less secure than VMs. Second, Docker is just a user-friendly wrapper around kernel primitives. The OCI standardizes these interactions. which is why the container ecosystem could move beyond Docker to lighter weight runtimes like Containerd. Third, containers are visible on the host system. You can see their processes, inspect their resource usage, and even interact with their file system layers. This transparency is powerful for debugging, but means you need to think carefully about security boundaries.